Hello, this is exam number 1. This is problem number 18. And I'm going to do different methods of working this problem. I think it's a very good problem for you to spend the time looking at this video and working through this because it illustrates a very common type of a problem. Okay, so here's the problem. If 1.5%, so 1.5%, that's the same as 0.015. So if 1.5% of the bolts made by a factory are defective, what is the probability that in a shipment of 200 bolts there are 6 defective bolts? All right, so that's the problem. Here's my standard technique of doing this. I write down first of all, I write down what we're given. So again, we're given that 1.5% of the bolts are defective. Find the probability that exactly 6 bolts out of 200 bolts are defective. So here's a little discussion that we start with as usual. I make a note to myself. I say, hey, wait a second. This is a binomial problem since the bolt is defective or it is not defective. So do you see that? If it's a 1.5% chance of being defective, it either is or it isn't defective. So that's why we would say this is a binomial problem. Well, n is 200, probability is 0.015, probability of being defective, p, is 0.015. Q, of course, is 1 subtract p, so that's 0.985, and then x is 6. If we're going to use the binomial formula, here's the binomial formula, okay? This is way too hard, okay? It's way too hard. N is 200. So we'd up on the top here, we'd have to do 200 times 199 times 190, excuse me, 200 times 199 times 198 times 197 and so forth. Over here, we would have to have a power of 200, or a power of 6 would be here. The power would be 6. Over here would be a power of 200 subtract 6. It's just too hard. It's just too hard to do it. So what we do is we do an approximation, okay? What I wrote here was it's too hard, but we can do it, maybe. All right, we'll see. So there's 2 options that we can do. Now this is exam 1, so the exam was supposed to be chapters 1 through 5. The Poisson approximation is in section 5-4, and it's on page 293. And in fact, example 5-30 is an example of how to do this sort of approximation. So that's right on point, right within our the scope of exam number 1. Now, for exam 1, I wouldn't necessarily expect you to do the normal distribution to approximate the binomial distribution, but by the time you watch this video, you've probably already gotten into chapter 6. So this is a chapter 6 technique. It's on page 354. It's section 6-4. So I'm going to go ahead and do both of these methods because that way, if you're when it comes time to study for the final exam, you will have both of these techniques that are available to you. Okay, so the Poisson approximation. Well, here's our formula. Probability of a particular value, x, given a particular value of lambda. Here's the formula, okay? X is equal to 0 or 1 or 2 or what have you. For our problem, we're talking about x is equal to 6. Oh, and by the way, up here, I believe I did mention where to go. It's page 293 of the textbook. Okay, so let's see here. The mean number of occurrences, well, this is a binomial distribution. So the mean of a binomial distribution is very simple to calculate. It's n times p. So n equals 200 times 0.015. Now, it's worth noticing as a side note that we see that the formula itself does not use n. So you come up here, there's no n here. So keep that in mind. I think that it's worth noting that. Okay, so if this is the formula here, what we want is the probability of getting 6 occurrences with a lambda of 3. So here's the formula. You plug everything in, relatively easy to do the calculation, and boom, there it is. 0.050. That's the answer. That's answer C. Okay, so maybe if you got that problem right, is that how you did it, or did you do it a different way? Let's take a look at another way we can do it, the so-called normal distribution approximation. Okay, so that's going to be coming up here in just one second, the normal approximation. But before we do that, I think it's worth a moment or two just to kind of help you understand what's going on here. Is always going to be is a very, very typical situation here. We're going to follow this common path on these kinds of problems. Whenever we're dealing with a normal distribution, so we follow this kind of a path, I guess I would call it. We start with a bunch of data. Okay, this bunch of data, these are what we're going to call the x values. And we're either told or we just assume that it's a normal distribution. Okay, so it has a normal distribution. However, the problem is it's too hard to figure out the problems. There's a normal distribution. The formula's in the book somewhere. If you look at that formula, it's just too hard. We just can't do anything with it. Now, in real life, we oftentimes will use a calculator, but for our purposes of learning this material, we don't want to just rely on a calculator. We want to learn how to do this stuff. So it's too hard to do this. It's too hard to figure out the problems. So that's a big frowny face. So what we do is we transform. We transform these x values, and we say, well, it's a normal distribution. I'm going to transform all of that data. Every single one of those data points can be transformed to have a standard normal distribution. Well, how do I transform it? I transform it to z values. A z value is just an x value, take away mu, divided by sigma. That gives me all of the z values. Well, the z values are normally distributed, but it is a standard normal distribution. And the advantage is this is easy to figure out the problems. How do we do it? We go to the tables. We have these tables that we're going to use that are right there in the book. So that's why we learn how to use these tables, because they're just so much easier to solve the problems. Okay, so to find the normal approximation, here's what we do. What we're looking for is the probability of x equals 6. So what's this probability? How do we, what we're looking for is the probability of getting exactly 6 defective out of the 200. So what we need is the mu and the sigma so that we can calculate the z value. Easy peasy. It's a binomial problem. Mu and sigma are easy to find. Okay, mu is n times p. Sigma is the square root of n times p times q. Crank that out. So here's our two things. We have a mu of 3, a sigma of 1 point, blah, blah, blah. Okay, so now we draw our cartoons. Draw the cartoons. In order to find the probability of 6, we have to do a correction for continuity. So what we do is we have a continuity correction. What we're looking for is between 6.5 and 5.5. Say this little area right here. Okay, so we're looking for the probability that x is between 5.5, between right there, and 6.5. Okay, well, that's too hard. So what we do is we transform everything to the z-score. So the z-score is this. What are the corresponding z values? Well, if it's x subtract mu over sigma, there it is. Crank it out. We've got 5.5 and 6.5. So it's 5.5 and 6.5. Okay, so we get those numbers. Okay, so now here's my new cartoon. I have a new cartoon. The z values are 2 point blah 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 and 1.45 blah blah blah. Okay, these are my two z values. I'm going to find this area right here. Now we can do it. Whereas before, I would have had to use this crazy formula that's in the book to find this area. It's too hard, so I transform it to z values. Now it's very, very simple. So the area to the left of 1.45 is some number. The area to the left of 2.03 is some number. Here they are. Here are the two numbers. How do I find those? I use the table. So it's, what do I have? 2.03 and I rounded this off, 2.04 and 1.45. So I go to my table. Here it is. 1.4, shoot, I forgot what it was. Give me 1 second here. It's harder than it looks to bounce back and forth here. It's one. I want 1.45 and I want 2.04. So 1.45, 1.45, 1.4, and here's the 5 right there. It's this number, 9265. And then the other guy is right here. Is well, I'm going to have to let you do this yourself, okay? I just can't bounce back and forth and keep it on the screen. Okay, so hopefully you've done a few of these exercises so you know exactly what's going on here. Okay, so we find those two areas, the area to the left of this guy, the area to the left of this guy. Here are the two areas. We therefore, this symbol stands for therefore. Therefore, the probability is you take this guy, subtract this guy. So 0.9793, subtract 0.9265. That gives me 0.0528. We round that off to 0.05. And that's the answer. So approximately, and as you can see, it's a pretty good approximation. The probability is 0.05, and that's the correct answer. So that's the probability of getting x is equal to 6 using the normal approximation. Okay. Now I want to make a note here. N is equal to 200. That's a large number. So we don't need to satisfy this condition. If you look at on page 354, for small values of n, there's a condition that you have to satisfy in order to do this. It has to be n times p is greater than 5 and n times q is equal to 5 if it is a small n. This is a large n, so we don't have to satisfy that particular condition. Okay, so finally, another choice we have is to use the binomial distribution. We're going to use a binomial distribution. We're not going to use an approximation. We're going to do it precisely. So here it is. We crank it out. Okay, we write all this stuff out, and we look at this, and then I give up. I just say to myself, it's too hard. This is too hard to do. 0.985 raised to the power of 194. It's ridiculous. It's just too hard. Okay, so I give up. So that's why we do the approximations. Okay, but it can be done. It's just too hard. I hope this helped. This is a video that I'm going to place in a couple of different places so you see the different techniques, in the various chapters and various locations. Thank you.